Okay, I did say in my last lecture we would be moving on to something really nice and new, but I forgot that we need to cover the Lewis structure, so let's do that real quick. Shouldn't take long, couple 20-minute lectures, just to bring you back up to speed and refresh your memories on how to draw Lewis structures, which of course are representations of covalent compounds, right? So you did a whole bunch of that in organic chemistry. You do all these squiggle lines, right? But the focus of my lecture will be on the heteroatoms, so phosphorus, sulfur, nitrogen, those kinds of things, atoms and their expanded octet and some higher geometries, not just tetrahedrons and pyramids. We're going to do square pyramids and hexagonal bipyramids, cool stuff like that. So you'll see some new things here in these next couple of lectures. Lewis structures were first proposed by Gilbert Lewis back in the 1900s, and it was a really simple technique that was able to explain some of the chemical composition of these compounds and give some insight into their structures. And he later on won the Nobel Prize in 1916 for his proposal or his technique. And so we understand that each line between two atoms represents two electrons. One, for example, here, if we have the carbon and hydrogen bond, we have an orbital with a single electron from hydrogen, most likely the s orbital, duh, right? And then a p or an s orbital, or maybe a hybridized orbital from the carbon here, and so, which also has a single electron. And so there's one electron from each element provided to make this single bond here. And of course, you must understand that these are electron clouds here. So these are really blobs, but drawing lines makes it much cleaner, and it shows us the connectivity between each atom here. You can make it look three-dimensional by making dashed bonds. For this one is going into the board, and then the solid wedge comes towards us, so it's not necessary, but it can be nice when you have more complex structures. And then dots on elements are representing electrons. Each dot is an electron, and usually they are paired up together in orbitals. Okay, so we can also, so we have a covalent bond. We also can have donor covalent bonds if, like, we understand that ammonia is a Lewis acid, sorry, it's a Lewis base, it's an electron donor. And then if we have something that has an empty d or a p orbital, like boron, we understand can be electron deficient. So BH3 would only have 6 electrons, but of course it does want to have 8 if it can, and it will, and it has, but it has to take up 2 electrons from an element with a lone pair, such as ammonia here. And ammonia will do just that. It'll donate the electron density into this empty p orbital, and so when we draw it all out, we don't really distinguish necessarily. I don't want to put a boron there, I want to put a nitrogen here, right? Nitrogen has a lone pair, and so when we draw it, it will look like this. Now every element here has an octet. Of course, hydrogen has 2. It doesn't need an octet, and at best we now indicate that we have charges here, positive and negative formal charges, but if we wanted to indicate that both electrons are coming from nitrogen, we can do that with an arrow, but we usually don't. So that's just the difference between a donor covalent bond and a regular covalent bond. Let's use SO2Cl2 as an example. We're going to go through all the rules on how to draw a Lewis structure. First step is to count the valence electrons. Those provide the number of electrons we can use for our skeleton and our connectivity. So pretty easy. Sulfur has 6, oxygen has 6, and chlorine has 7. Of course, we have 2 oxygens and 2 chlorines. We multiply it all out. That's 32 electrons. That's what we have to play with, no more, no less. You know, you can't add and subtract electrons. So you must use them all up and then make sure you get an octet where needed and reduce formal charges. So what goes in the center? Sometimes it's pretty intuitive. You probably would put sulfur in the center anyway, but there's a reason for it, right? We want to put the most electropositive in the center, which happens to be sulfur, right? So positive means it doesn't want as much electron density as the more electronegative elements. So oxygen and chlorine are more electronegative. They are more likely to pull electron density towards it, right? So think about it, if you had a very electronegative element in the center, it would pull all that electron density towards it, and it would crowd it, and maybe some of these atoms couldn't bind. So there's, if you do have a choice, like if you have SCN minus, what do you put in the center? Well, carbon probably, right? But it could be nitrogen or sulfur. You have to make a decision, and the most electropositive is what is chosen, which is sulfur in this case. Anyway, we'll come back to that or think about it while we're gone. All right, so once you've counted the valence electrons and you've decided the connectivity, select the central atom, take all of the other atoms and surround them. 99 out of 100 examples we do will be exactly like that. We will have a couple where you have a more complex structure. We have to have more than one central atom. We'll look at those possibly, but for now we'll just use that. Then you assume a single bond between the remaining atoms, which consumes, in this case we've made 4 bonds, so that consumes 8 electrons. So we had 32 valence electrons. We've used 8 up for that leaves 24 remaining atoms, or elements, sorry, elements, atoms, okay, electrons, of course. And so we spread them out from the inside and out, filling up an electron. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Those are the 24 plus the 8 from the bonds. And so I stop. Next thing is you check for an octet. And so we have an octet. The chlorine, oxygen, they all have an octet. The sulfur in the center, I'm going to color code this in red, this also has 8. Gets a little nastier now, or just a little bit less clear, but it has 8 shared electrons. So that's fine. So that's a reasonable structure to propose. However, we do want to reduce the formal charges. Now, the formal charges can be calculated by the valence minus the lone pair electrons plus half of the shared electrons. So this is for each atom, right? Like oxygen here has a valence of 6. It has 6 lone pair electrons, and it has 2 shared electrons, and so then half of 2 shared electrons gives me an overall -1 charge. So oxygen here, singly bonded to sulfur, has a -1 charge. So it's the same thing over here, and the 2 chlorines have 0 because they have a valence of 7, and so they then also have -6 plus half of 2. That would give it a formal charge of 0. And the sulfur in the center has a valence of 6. It doesn't have any lone pair electrons, and then it has, of course, 8 shared electrons, and that gives it a +2 charge. Now, a +2 charge next to a minus charge, having a -1 charge next to a +1 charge is not a big deal, but having a +2 charge, that's too high. So we need to try to make these charges, reduce these charges. So that can be done in this case for sulfur, because sulfur can have an expanded octet. Now, the double bond that we're making here is no longer made between a hybridized sp3 orbital, right? It's now actually done with a d orbital, right? Because we have, if you think about it, the bonding orbitals are s and then px, py, and pz. So we have 4 orbitals, and so we can make, with these 4 orbitals, we can make 4 sigma bonds. We can easily say, okay, that's not a problem. Here they are. But how do we argue that we can make a pi bond now, which needs to be an unhybridized p orbital, which we don't have? We have, these are all used up. So we must use another energetically available orbital, and so sulfur can access the d orbitals. So sulfur can do that, but oxygen cannot, nitrogen cannot though. So the second period elements, they also have d orbitals, but they're much higher in energy and not available. So you will never see carbon make 5 or 6 bonds, but silicon underneath it can easily make 5 or 6 bonds. The other interesting part about silicon versus carbon is carbon will make double bonds and triple bonds, but silicon will not. So So they're in the same group, they have the same number of valence electrons, but they're drastically different. So the point here is we can have an expanded octet, we can make double bonds, and we can reduce the formal charges. And when we can do that without crowding the central atom, we do it. Okay, so we can make 2 double bonds here to reduce the formal charges all to 0. And that's a very important rule. So this is the most plausible or best representation of S2O2Cl2. Okay, so those are the rules. You're now ready to practice. Let me just point out a couple things, a couple of easy examples here. Of course, if you have a polyatomic ion with a charge, you have to either add or subtract valence electrons here, right? So we have 5 for nitrogen, then we have 4 times 1 for the hydrogens, and then we are actually subtracting the charge. So we end up with 8 valence electrons. Nitrogen goes in the center. This is going to be super easy. There isn't going to be any issues. And then if we do formal charges, we do end up with a positive charge on nitrogen, which is fine because we have to have it, right? We have an overall charge. So in this case, the formal charge corresponds to the overall charge of the polyatomic ion ammonium here. So hydrogen does not need an octet, but nitrogen gets that octet by sharing. The other example is sulfate. So sulfur and oxygen both have 6 valence electrons. So I'm just going to do 5 times 6, which is 30. And then I add the 2 electrons from the charge to it, right? So this is 2 electrons have been pumped into this molecule to make it work, to give everything an octet. They are needed. So that gives us 32 valence electrons. We put sulfur in the center. Oxygen is much more electronegative. It's more likely to be on the outside. We assume single bonds to these oxygens. That uses up 8 electrons, and when we spread out the remaining 24 electrons, we spread them out from the outside to the inside. So sometimes we have some electrons left over, they can go on the inside. And we move on once we fill up an octet, right? So we know oxygen just needs 3 more lone pairs, so we move on. And when you do this, you end up with 6 lone pairs, no, 6 electrons, or 3 lone pairs on each oxygen, which we know gives oxygen an octet, and sulfur as well has an octet. When we do the formal charges now, every single oxygen has a -1 charge. And again, the sulfur in the center has a +2 charge. So that may be okay for Gen Chem, but it's not okay for advanced inorganic chemistry or even for organic chemistry. This sulfur has the capability of engaging and bonding with its d orbitals, its 3d orbitals. And so we'll do just that. It is going to make 2 double bonds. So if we make 1 double bond, let's just start out like that. That took me a while. Maybe I'll edit that a little bit. But now we have a -1 charge, -1 charge, 0 charge, and a -1 charge, and a +1 charge. So we reduced formal charges. We can do the same thing with 1 more. So let's do that. Here we go. I did some magic there just to save some time. So that puts the 0 here and a 0 here. So that's excellent. Now we cannot get rid of those. You can make another double bond, but you'll put the negative on the sulfur, which is not a good idea because we know the negative needs to be on oxygen. It is more electronegative. Plus you would have 2 -1 charges next to each other, and that doesn't work. We do need to have those charges, so this is the most plausible structure. So at this point, I asked this question. So what I've drawn here on the right is a resonance structures. It simply has the electrons distributed differently. And I always ask this question, and I won't be able to do the same type of drama that I do and drag it out and get people engaged. But just think about it. Would there be an advantage over one or the other? And so intuitively, you're looking at a 2-dimensional surface. A lot of people will say, oh, this over here is preferred because you're spreading out the double bonds, and so, but you got to keep in mind that this is a tetrahedral, that the bond angle between these two doubly bonded oxygens is 109.5, and that this here is also 109.5. So in it's sometimes very difficult to go from a two-dimensional surface to a three-dimensional idea molecule, and so you got to keep this in mind. You know this is a tetrahedron and the bond angles are 109.5, so there's absolutely no advantage over having the double bonds distributed differently. These are all identical resonance structures. So I did two examples. Now I'm just going to highlight some things you need to watch out for when you are, first of all, when you are reducing formal charges. You can't really do that for nitrogen, right? You cannot put, you can reduce the formal charges, but you can't put 10 or 12 electrons on nitrogen. It can only have 8. And sulfur can in this case. So let's see what we can do. But so absolute no-nos are the 2+ charges here next to each other. That is not going to happen. So they need to distribute or be minimized. And so you can draw a cyclic structure. There's some ring strain you gotta worry about, and it is, if you have to, absolutely have to have a plus and a minus. It happens as long as you have an octet, and also the electronic trends are holding true here. Nitrogen is more electronegative than sulfur, so if you could somehow get that plus charge over here, that'd be good. And you can play around. Look, I have it arranged differently. Here I have the 2 sulfurs in the center, and here I have them spread out. And then if you get rid of all the formal charges, make sure you don't do a boo-boo like I did here. This is great, all the formal charges are reduced, except nitrogen now has only 6 electrons, so that can't happen. So we must make a double bond here. Okay, and go back to the structure. So that's something to look out for. And again, the electronic trends, if you have charges, the more electropositive here, nitrogen should have the positive, and the oxygen should have the negative. So both of those structure, as far as formal charges are concerned, are equal, right? We have a minus and a plus next to each other. It is just more likely for oxygen to have that negative charge. So this right here is the more reasonable structure. This reduces all of the formal charges, except again we have blown the octet rule. Nitrogen cannot do that. All right, so again, octet rule, you can't have things, so then you might have to rearrange. Since you can't make any double bonds here, you will have to rearrange your connectivity if you get to a dead end. Always, don't ever break that octet rule. The exceptions, of course, are boron. Can have 6 electrons, and you'll see in a minute that's not quite true in reality. In reality, boron will fill its octet one way or another. That empty p orbital is going to get electrons. Because of that, it's pretty reactive. So, okay, so make sure the octet rule is followed, and then, oh, here we are going to talk about it, right? So it's very interesting, because what boron will actually do is boron will dimerize, as I said. We're going to draw it this way. Okay, so we have 3 sigma bonds here, and we still have that empty p orbital. It does want to get filled. And so what boron will do, borane here, BH3, which is a gas, it will form a dimer. And so this is actually going to be new. It will actually take the electron density from the sigma bond of the boron hydrogen to donate into this empty p orbital. I'm going to draw it right here. Okay, so this should be pretty new to you, that you can actually have donation of the sigma bond electrons into an empty p orbital, right? So we call that a 3 center 2 electron bond. Okay, and so it'll do the exact same thing here. All right, so it's really that. So you don't have any more. You still have 6 valence electrons here for each, so a total of 12. And so we draw it like that. And so you see this dashed line. But again, this really is coming from the sigma bond here. Those electrons are donating into that p orbital. So boron is not going to be very happy with 6. And GenChem boron was happy with 6. And inorganic chemistry boron is not happy with 6. But expanded octets, right? So never ever do that for the second row. That's important. The d orbitals are just too high, but we can definitely do this for silicon, phosphorus, chlorine, right? So if chlorine or bromine, of course we expect those to be just having a single bond, right? If they are connected to nitrogen, for example, we expect those to have a single bond and be terminal, but there are those where they are central atoms and they're bound to oxygen, like in chlorate, ClO3-, and we'll do this in a minute, or perchlorate, ClO3-. So now you can have chlorine as a central atom, and you can have, it'll have multiple bonds, at least 3 to oxygen, right? So it can also have double bonding. It can have that expanded octet. And then you have the analogous bromo compounds, right? If this is, I wanted to do Cl4 perchlorate. So you have analogous bromine compounds, BrO3 bromate. So where bromine is the central atom. So those can also do expanded octets and have multiple double bonds if needed, right? Again, it's about the formal charges. Discard ring structures with strain, right? So you know you can have epoxides, you can have 3-membered rings, but if you can come up with a plausible structure that doesn't have ring strain, go with it. So right here, S2O, this would be more reasonable than a ring, okay? Although we do know rings do exist, 4-membered, 5-membered, 6-membered, etc. Okay, resonance, have already mentioned it. Here, resonance, NO3 nitrate has 3 resonance structures. I'll draw them real quick. Magic, here they are. Anyway, these are all equivalent structures. These are 3 resonance structures. It's just that these electrons do distribute. By the way, if you Google nitrate resonance structures, you're going to get an incorrect resonance structure. You will find one where the formal charges are reduced, and I just explained to you that that doesn't happen. So there will be 2 double bonds, right? Because if you think about it, you have -1, -1, and +1. You may want to do a double bond, but you can't because nitrogen cannot utilize the d orbitals. But it is true that, you know, it wants to get rid of this charge. So it is going to try to do this. But when it does that, it's going to have to push one of these up. So that's kind of a driving force too between these resonance structures. Those electrons do constantly move around, which is perhaps better illustrated up here with my ozone representation, but we have the same thing here. We have a -1 and a +1 charge, and then this is 0. So we will have this sort of thing going on where this constantly pushes back and forth, and so that causes this resonance. And this process is so fast that we sometimes represent the Lewis structure for these types of compounds like that, where we really have, now we have the positive charge on the oxygen, and that negative charge is actually distributed here between these 3 evenly, right? So you don't really have a -1 and a +1 here. You really have, if you wish, like a -1/2 or and a -1/2 here, but it really is that negative charge is distributed over those 3 bonds. And so the same thing is true here. And the bond order too, right? We don't have a double bond and a single bond. And you organickers, you know that, right? We don't have cyclohexatriene. This is not, we don't have a double bond and a single bond. We don't have a short bond and a long bond. These all have bond order of, these are all the same carbon-carbon bond length, and they are somewhat in between because this is aromatic, right? They're somewhat in between first and second order, right? And so they're like a bond and a half. And so that's something that you also want to keep in mind, that the reality is that these electrons are distributing. But warning, you should, I dare you, go ahead and Google that. I bet they still haven't updated it. You will find the resonance structures where nitrogen has 10 electrons, and that can get you in trouble, at least on my exam. Isoelectronic just means the same number of electrons. If you have two molecules with the same number of atoms, like ozone and nitrile chloride have the same number of atoms, the same number of electrons, they will be isostructural. They'll have the same Lewis structures. Pretty simple here. This is pretty much it. At this point, you have got to practice that. Here's a ton of you to practice. Those are simple with central atoms. I also ask for hybridization of the central atom as well as the molecular shape. That's in the next lecture. But so for now, just practice drawing these Lewis structures. If you want something more complex, as would be appropriate for an advanced inorganic exam, right? So I'll have at least one that's more involved. Try playing around with these. Most of those don't just have a single central atom. They're connected, and since they don't have carbon, they'll be hard for you since all you have is organic chemistry, right? So shouldn't have any trouble. Follow the rules and the recommendations in this lecture. All right, so let's do this structure just to finalize everything. And we're not going to do formal charges by calculating it. We're just going to draw it. We're not even going to count valence electrons. We're just going to try to minimize the formal charges and see if it's right. So I would put the chlorine in the center. I would look at a single negative charge, which means I'm going to have a single oxygen, single bond. That's going to put a negative charge on there. And then everything else, all the other ones are going to be doubly bonded, because I know when I double bond an oxygen, I get a formal charge of 0. Okay, and then what I do is I look at the formal charge of chlorine, and so I have 1, 2, 3, 4, 5 electrons on there. Right now, as it is, I would have a +2 formal charge. So I simply add a lone pair of electrons, and I call it a day. And I just saved myself 7 hours of agony. So keep that in mind. See you for Vesper theory.